Hello everyone, my name is Andrea Cacioppo, and today I'm presenting our work on the paper Efficient Graph Coloring with Neural Networks, a physics-inspired approach for large graphs. In this poster, we'll introduce a novel algorithm based on graph neural networks to tackle the graph coloring problem. And in particular, we will see how our method outperforms simulated annealing, which is a widely used and standard classical non-machine learning method for solving the graph coloring problem. Let me start with the problem statement, which is actually very simple from a theoretical perspective. Namely, we have an undirected graph G made of nodes connected by edges, and we have a set of Q colors. In our paper, we explored the case of Q equals 5, so 5 colors. And the objective of graph coloring is to assign a color to each node in such a way that the number of neighboring nodes sharing the same color is minimized and ideally 0. Mathematically, this is equivalent to finding the ground state of the Potts Hamiltonian, which is the generalization of the Ising Hamiltonian to a system made of particle with Q spin states instead of 2. To tackle this problem, we propose the physics-inspired algorithm that uses graph neural networks as its backbone, and in particular we use a version of graph neural networks called message passing networks. These networks are basically graph neural networks for which both the function that generates the messages between the nodes and the function that updates the final node features are learned by two neural networks. In our architecture, as shown in this figure, message passing is performed k times, storing the intermediate representation of each node. In other words, this architecture can be thought of as a k-layer message passing network. However, we don't just take the output of the final layer, but rather we store the node's intermediate features at each layer, and at this point, in order to use all this information, for each node we concatenate all the intermediate features at different depths, so the resulting graph with expanded features is then passed to a final multilayer perceptron that produces the final graph features. This output is then used to compute the loss function. And speaking of the loss function, in our algorithm it is made of two terms. On one hand, an unsupervised term that counts the energy of the system, where each conflict gives an energy contribution. In this case, however, we don't use the classical Potts Hamiltonian, but rather a differentiable version of the Potts Hamiltonian. On the other hand, we have a supervised term called the overlap term that increases the loss value based on the difference between the solution found by our model and the ground truth solution. And in our case, in order to have the ground truth, namely a graph which is already solved, so a graph with no conflicts, we created graphs using a technique that comes from statistical mechanics and is called quiet planting. For this study, our dataset was made of 26,000 graphs spanning different connectivities, and each graph having 1,000 nodes. Once the model is trained, a single pass of the neural network is sufficient to find a good coloring. However, we have empirically observed that the performances can be greatly improved if, instead of using a one-shot approach, we use the trained model in an iterative way. In particular, the final version of our algorithm uses the trained graph neural network to solve the graph by calling the graph neural network actually several thousand times in a loop. And as shown in this figure, each time the output of the GNN is corrupted again with noise and fed back to the same graph neural network. And this is done for several thousand times, diminishing the amount of noise each time. And at the end, this produces a much better solution. And intuitively, this is analogous to using test time compute when using large language models, where basically one can trade the speed of the solution for the quality of the solution. So better solutions require more time. As seen in these figures that compare the performances of our model versus simulated annealing, our model outperforms simulated annealing in a vast region of connectivities of graphs. On the left side, we report how the fraction of conflicts in the graph varies with the number of coloring steps for two connectivities, 13.5 and 11.5, while on the right side, instead, we see the result of 3 different fitted parameters. In particular, we have found a very good agreement when using this formula to predict the percentage of conflicts from the number of iterations. And what we see is that for all connectivities below 15, our model scales better than simulated annealing in all 3 parameters. So in conclusion, our work is a demonstration of the feasibility of a physics-inspired graph neural network approach. And we show how, by exploiting quiet planting for training and using a noise-based iterative approach for coloring, this model outperforms simulated annealing on large regions of connectivities. And in fact, on this dataset is able to beat all the other available AI-based methods.